Hello everyone, in this video I'm going to go over how to run a basic PySCF calculation with a supercell transport calculation. This video is just going to cover our current calculator and the script that we use with a basic PySCF calculation. We are going to make a second tutorial going over more advanced settings with the PySCF and what each of those settings do, how to change those, and what they will impact on your calculation. But for this video, it's just going to be a basic PySCF calculation. Since this script is so nice, you do not need too many things for this. You do just need your .py script and your .xyz file, so it is very simple. I'm sure at this point you have seen an XYZ file. I just like to go over it just to show some examples. So the XYZ file that we're going to be looking at today is the lithium wire. The reason why we're choosing that is because it's very simple and it runs very fast, so this is a great example to show, but I will also be showing you an example of a molecular junction, something that you would kind of expect to see in our research group. So, first thing that you're going to do is take your XYZ. Now this is if you're being given an XYZ or you make one through Google Sheets. So what you're going to do is you're going to copy it, then come to just a document or a notes app or anything that you can use just to kind of get the data written down. You're going to click paste without formatting. The reason why we don't do pasting with formatting is because if we do that, it's going to look like a spreadsheet, which is not what we want. Avogadro and our script will not be able to read it that way. So another thing that is important to note here is that this is separated by tabs. So in order to fix that, we're going to go to Avogadro. But what I like to do before I run any of my calculations, I do just like to go onto Avogadro to check the XYZ because mistakes happen, which can completely ruin calculations. And we just want to check to make sure that there are no mistakes. So we're going to go to Avogadro, which you can download on your computer, and they, I believe, are downloaded on most of the computers in our lab in Robinson, but if it's not, it's very simple to download. It doesn't take up a lot of storage, which is really nice. It's a really great program for us to use to visualize our molecules. So what we're going to do is click on our Avogadro program, select build, click Cartesian editor, and then here we want to click sort by X. That's going to be really important because if we don't sort it by X, it can cause errors in our calculation because it's usually reading the XYZ file top to bottom. So what's going to happen is if that it's not in the correct order, it's going to read it incorrectly and then it's going to get all sorts of messed up. So just to avoid that, we click sort by X and then we're going to paste here, click apply, and then go back to the screen here. Now to view it, you're going to click on this button here. You don't have to do this on Avogadro 2 if you are using Avogadro 2. But Avogadro 2, I don't believe, has a setting where you can sort it by X. But yeah, so you can zoom out, you can play around with this, and look at your molecule. Looks good, right? So then we can say that this XYZ file is ready to go. So then we're going to go here, click Cartesian editor again, then we're going to highlight, copy, and paste. So now your XYZ file is ready for computing, which is great. I'm going to run through that one more time, just showing you a system that we more commonly use in our group, which is a molecular junction. As you can see here, there's a bunch of metal here, and then in the center of that, we have a molecule, and then there's more metal. So what's important to note on this is we want the left electrode to be negative in the X direction, right? Because you want your molecule to start at 0, 0. So you can see here, the sulfur linker is at 0, 0, 0. We read left to right, as does this program, so we want to make sure that it is reading our stuff properly. So just to go over what we did again, we're going to copy, go into a document, hit paste, all the way up, copy, go into Avogadro, build, Cartesian editor, sort by X, paste, apply, and there we have our nexus. I don't know why it does this. Whenever you paste something new, it'll sometimes show you the screen of the old thing, but if you restart your Avogadro, it won't do that. So there's our system, right? So our left electrode's here, our molecular center's here, and our right electrode is over here. Great, so we're going to go back into build. Everything looks good. Cartesian editor. And then we're going to take this, copy, paste, and there it is, all organized and looking beautiful. We have spaces in between here, which is great. It is also important to note that because we're running a supercell calculation, we want our electrodes to be 3 layers. So as you can see here, this is layer 1, layer 2, and layer 3 on both sides. So that's just something to keep in mind. If you are running a supercell calculation, you do want to have at least 2 or 3 layers, depending on which metal you are working with. That's something that you can ask Dr. Hoy about, but usually you want to shoot for 3 layers if you are working with a molecular junction. Alright, so now that we have the XYZ file set up, what we're going to do is put the XYZ file into the directory in which we want to run our calculation in. So I'm going to go on to RDM3. Okay, so I'm going to go into data, my name, and then I just did like a little tutorial section. And then I'm going to VI and whatever you want to call it. So I'm going to call mine LI wire. And then you're going to put .xyz. Okay, so now I'm going to copy. You're going to click I on your keyboard, then you're going to right click. It's going to ask you if this is what you want to paste. You hit OK. Okay, and now the next thing that we need to do is we need to tell the computer how many atoms there actually are. So you want to give it a number. So how we can do that is we can either manually count it, but when you're working with something that looks like this, manually counting it is no fun, right? So what we're going to do is we're going to scroll down here, and it will tell us actually how many lines there are in the code. So there's 14 lines, that means that there's 14 atoms, so we're going to space down here, put 14, and you always want to make sure that there's a space between the number of atoms and your first atom in the line. So now what we can do is we can save this, and now we can move on to talk about our PyRUQT script for PySCF. Looking at the PySCF script, Dr. Hoy actually did a really great job with this script explaining what everything really means, but I'm just going to briefly go through it so we can kind of run through setting one up together. So the first thing is just inputting the PyRUQT. That's all good. That's already written in the script. We don't need to change that. What we do need to change is the output name. So what I want to name my output file, I want to name mine just LI wire. I like to keep them the same as the XYZ. I tend to run into less errors that way. Then here, it's the XYZ directory, so where you can find your XYZ file. For these calculations, I like to put them in the same directory. So we just put a period and a slash, which basically tells the script and the code, hey, it's in this directory. If it were to be in a different directory, you would put that directory there. Then it's asking for the XYZ file's name. So ours is called li_wire. So that's that. And then it has the XML program, which is just PySCF, the electrode program, which we're using supercell, the basis set, which usually pertains to the electrode and its metal and what basis sets work best for those. Usually Dr. Hoy will kind of give you what basis sets to use, but it's very easy to look online. For instance, if you look up gold best basis sets to use, it'll give you a list of a few that you can try out. So the ECP is an effective core potential, which basically you can add those depending on which basis set that you use. I know for LANL2DZ, which is used for gold, there is an ECP, but in this situation we don't need to use it. Now, the PySCF settings are what is important here, and this is what Dr. Hoy has thankfully done a really great job in setting out for us. So the first thing is whether you want to do MCPDFT or DFT. This is something that you can kind of do trial and error with and see what you can get to converge and what you'll do the best results. Here we're just using MCPDFT. The next thing is if you're doing MCPDFT, whether you want to do CAS-SCF or CAS-CI, and if you put DFT, it does nothing. The next thing is the active space. What we found is that the bigger the active space that you use, the more accurate results that you'll get. But again, this comes with a cost because the larger active space that you have, the longer that the calculations will take. So in this example, I just do a 4x4 because it works okay for this system and it's just to get a quick calculation done. I personally use a 12-12 active space, which is fairly large, but that's because we are using very large electrodes, so you kind of need a little bit of a bigger active space there. Usually Dr. Hoy will give you a number to kind of start out with, but those are the ones that we commonly are using. Now the next thing is the type of SCF solver that you want to use. The first one that you can use is restricted Hartree-Fock. And then the next one is restricted cone jam, which is a restricted DFT type of SCF solver. I usually use restricted cone jam, so I keep that there. But if you're having trouble with conversions or anything like that, you can switch to the restricted Hartree-Fock and see if that can work for you. The next thing is the DFT functional that you want to use. We tend to run most of our calculations in PBE. Again, if Dr. Hoy wants you to change that, he will usually let you know. Again, this might be something that you can play around with if you're having SCF conversion issues. And then finally, the last thing is the amount of PySCF output printed. We usually keep this the same. We don't really mess with that. Now, before I go on to the rest, there are more settings, but in this video, because we're covering a pretty basic PySCF calculation, we will go over more advanced settings in a separate video. So this is just for the basic stuff. Now, one of the most important things here is the electrode size, which is here. I have highlighted in green because it's so important. That is a number which we currently have to use the basis set exchange website to get the number in which we want to use here. In this calculation, since we're just doing a lithium wire, we're just keeping at 1010 just to keep the calculation running smooth. It's not a super large supercell. It's very small, so the number doesn't impact it too much. But if we were to do something like gold, this is where we have to start to worry about it, right? So how we can get that number for gold is on the basis set exchange website. Let me just expand this a little bit. When you open it, I'll restart it so you can kind of see. You're going to see a periodic table in which you're going to select the atom that you're working with. So we're working with gold, so I'm going to select gold. And now I'm going to set the basis set in which we are working with here, which is LANL2DZ, if I can find it. Yep, LANL2DZ. Now, it's going to format it in NWChem, so you're going to click Get Basis Set. And what you can either do is you can either count the rows, or you can just simply count these first numbers here. And you're going to add them together, and that will be the number of orbitals in each gold atom. So we have 5 plus 6 is 11, plus 3 is 14. So we have 14, so we have 14 per gold. And in each layer of the gold electrode, there are 10 atoms of gold. I'm going to say per layer. And in these calculations, we usually want to represent 2 layers. So we'll say 2 layers total. So we would do 14 times 10 times 2, which is equal to 280. So for gold, electrode size will be is 280, 280. So that's what you would input here. To finish this off, the convergence tolerance we usually keep to somewhere around this number. And then the minimum transmission energy, we usually do either -2 to -5, and then for the maximum we do 2 to 5. Okay, so now that that's done, we can move on to finally running the calculation and analyzing the data. All right, so now that we have our PySCF script completed, what we're going to do is we are going to copy and paste that into our directory. So first we need to make a file that will be called the name of whatever we're going to do, li wire, and you're going to call it the name.py. Now we're going to do the same thing, press I on our keyboard to insert. You're going to copy and paste. You don't need to copy and paste this stuff down here. What's most important is this information here. So we're going to right click, everything looks good, we're going to hit OK, then we're going to save that. Now to run the calculator, again, all we need is the .pi and the .xyz. So now to run it, what we need to do, which is described here, we're going to type no HUP, which this basically tells the calculator, do not stop running the calculation when we exit the terminal. Because sometimes these calculations when you're working on big systems can take a few days to run. So when you exit the terminal, you don't want it to stop, right? You want it to keep going for those few days that it needs to run. So no HUP, then we're going to type Python, and then the name of the Python script, an ampersand, and then we're going to do a greater than sign, li wire, and now .log. So what the .log is going to do, it's going to basically write down all of the output into one file so that you can check to make sure it is running smoothly. And sometimes errors will pop up on there. It's a really great file that will just gives you a bunch of information. So it's not really necessary for running the calculation. It will run fine without it. What it's necessary for is your own basically peace of mind for checking your calculation and getting more information about your calculation if it fails. You can kind of predict possibly how long it's going to take. You can look at your SCF energies to see if it's going to converge, etc. So once we have that done, we do another ampersand and we run it. Click enter, so now it is running. This is a really quick calculation, so it shouldn't take really too long. So it created a moll.dat file, which that tells us that the SCF ran and it converged. So now what it's going to do, it's going to take that moll.dat, run the transport calculation, the supercell calculation, which it should be done in just a few minutes here. So yeah, very quick calculation. This took maybe 60 seconds. But again, when you're running a bigger system, it will take more time. We can view the conductance, and you can take what you need from your conductance to analyze your trends. We can look at the transmission. You can plot this, and this will give you information on the electron transport. So now to view the .png files, what you're going to do is type display and then the name of the PNG file which you want to view. So I pulled up the transmission, which looks very similar to what we would expect. This is actually showing about a 2-electron transfer, which is what we're looking for. But for systems, possibly if you're running a new system, for instance, the gold acene chain systems from the examples that I was showing you, that you want to do a little bit more of a literature search to kind of determine what your expectations are for those calculations and what those results may look like. So that's the whole video. Hopefully this clears up some things about how to run the calculation, gives you some more information on PySCF as a whole. But yeah, thank you all for watching, and I hope your SCF energies converge, and good luck.